Hi, welcome to Unit 5, Biochemistry unit. And we have 3 lectures left, unfortunately. I have basically condensed all the lectures as much as possible. Free radicals is one of the topics that I feel is very important that you should know about. Hopefully I will be able to cover this in 3 of these video lectures. If you're interested in this topic, chapter 11 in your client has a very detailed description of free radical chemistry, and you're welcome to dive into it. All right. So free radicals is so important. The reason is scientists feel that ozone hole is responsible with free radical chemistry, and some scientists believe that aging and cancer may be caused by free radicals. And then the lab that you're doing where you're making polymers, that is done by free radical mechanisms. So I feel that you have to be at least exposed to this chemistry. All right. So far, all the reactions that you've studied are, I would classify them under polar reactions, because all the reactions involved 2 electron movement. All right, so far the reactions were polar reactions, and the reason for that is 2 electrons were involved. In the bond breaking and forming process. All right, so for example, if you were breaking a bond, we used a 4-headed arrow to indicate that the 2 electron has now so if there's a bond between A and B, and we're breaking that bond, then we gave to let's say B, then A would have a positive charge and B would have a negative charge because it got the 2 electrons, right? Another way we looked at that would be bond breaking process, but if we were to have B minus go and attack A plus to form this bond, then we would do a reverse reaction, which would be bond forming reaction, right? But either way, we use a 4-headed arrow to indicate movement of 2 electrons, right? So, and a lot of these things were, for example, the B minus were nucleophiles we abbreviated as, and the A plus would be electrophiles. So a lot of the reactions that we looked at so far were polar reactions in which electron-rich atom was attracted to electron-poor species, an electrophile. All right. So free radical reactions are totally different type of reactions. In these reactions, bonds are formed or broken, but they're not polar species that come together or come apart, but the species that does this are free radicals. So in order to understand free radical chemistry, we have to define what free radical is, and then kind of get a sense of the type of free radicals that are out there, and then compare and contrast the stability of these free radicals. All right, so let's define what the free radical is. Free radical is an atom or group of atoms with an unpaired electron. All right, So let's compare that to ions. So if you were to write an ion, bromine ion, for example, and if you were to look at all the electrons that it has, then it would be a negative charge with 8 electrons around it to fulfill the octet role. And we usually don't write all the electrons, but we abbreviate it as this, but you know that that's what this means, right? So free radical, a bromine free radical would be different in that instead of having 8 electrons, now it would have 7. And here's the unpaired electron that we were talking about. So this would be a bromine radical. And it doesn't have to be just an atom that could be a radical. It could be a group of atoms. So for example, a hydroxy radical would look like this, where once again, you have an atom with an unpaired electron. You could even have an organic radical, a carbon radical. So for example, a methyl radical will look like this. All right. So a lot of these free radicals are abbreviated in a shorthand form. Instead of writing out all the electrons, the only electron that is shown is the unpaired. So for bromine, Br dot would be a shorthand way to indicate a bromine radical. A hydroxy radical would look like this in an abbreviated form, and a methyl radical would look like this. And so you would always show a dot where the unpaired electron is at. All right. So in showing electron movement, so for example, forming free radicals usually happens when you have something to cleave it, and a lot of times the UV light is strong enough to do that. And instead of using, so when this 2 electron comes apart, what happens is each of the chlorine atom gets 1 electron, and that's indicated by this single-headed arrow. So let me just write down the single-headed arrow. That indicates 1 electron. So so that's a movement of 1 electron. So notice it's not a double-headed like you saw here, a full-headed arrow. That's indicating 2 electrons here. But here, a single-headed arrow is indicating 1 electron movement. So that means that in this case, the 2 electron is split apart homolytically, where each chlorine atom gets 1 electron each. So that's how you would indicate a bond homolytically being cleaved. So that just means that the 2 electrons given equally to each atom rather than 2 electrons going to 1 atom. All right. Now, if you want to indicate 2 radicals coming together to form a bond, then here you would just draw a half-headed arrow to indicate that you're forming a bond between the 2 radicals. All right. So that's how you would show the electronic movement. So as you might have guessed, since these species have an unpaired electron, what do you think are the characteristics of free radicals? All right. You might already guess that these are going to be very reactive, and that's true. And they're going to be very unstable because it's going to want to have another electron to fulfill the octet rule, all right? And the reason why they're reactive and unstable is because the electron deficient characteristics. So due to electron deficiency, as you might have guessed, and they're gonna tend to be electrophilic, in its reactivity, and because they're unstable and unreactive, they're going to be very short-lived. So they're going to be very hard to isolate and study, because as soon as it's formed, it's probably going to want to react. So those are the characteristics of most free radicals. So we're going to now look at more in detail the carbon radical, and that's shown in the picture here. The carbon radical is the carbon, scientists believe is sp2 hybridized. There's some controversy as to whether it's sp3 or sp2 hybridized, but a lot of people believe that it's sp2 hybridized. Okay, so that means that you have 3 of the sp2 hybridized here, shown in this plane, and this orbital right here is the p orbital. That's orthogonal to the sp2 hybridized orbitals. So think of it as if you're looking at the carbocation, then the p orbital would be empty, in a carbocation. Here in the carbon radical, the p orbital has 1 electron density in it, as you can see in that dot. All right, so that's how you could look at it. And so what would happen if you react the carbon radical in which you have, let's say, X, Y, and Z as the 3 components that's attached to the carbon, and you're reacting with a chlorine radical, right? And you're gonna form a bond between this carbon and chlorine that is different, and let's say it's not X, Y, and Z are not chlorine, and you're forming a chiral center at this new carbon, then what's going to happen is that you're going to form a racemic mixture, because let's try to draw Y, X, and Z, because the chlorine radical could attack this p orbital equally from top or the bottom. And you would have this plus the enantiomer, and so you would get a racemic mixture. All right, so you should be able to do 11.1, 11.2, 11.3, and 11.5 at this point. If not, then just wait until the next lecture to do these problems.